Swayam Prabha. Digital India. Educated India.
Let's now take a look at sequential logic. So sequential logic is slightly different from combinational logic. So here the idea is that we save a value in a structure and then we do some amount of computation on it. So this is called a logic cloud, right? We have a lot of gates and so on. And then again, the output of this is again stored in another storage element. So the first question that we need to answer is that how do we store a single bit, right? How do we ensure that we are able to store a single bit and the value sort of remains for as long as we want to keep it. So the idea is that to store a bit, we use a cross-coupled pair of NAND gates, and that will store a stable value. So this particular structure over here is called an SR latch, and so S stands for set. So what does set mean? Set means set the value of the output, which in this case is Q, to 1, and R means reset. Reset means set Q to 0. So the SR latch has two inputs, which is basically the complement of S and the complement of R, and the output, and there are two outputs. One output is Q and the other is the complement of Q. So in a sense, it's a single output but available in its normal form as well as its complemented form. As simple as that. And why do we say it is cross coupled? The reason being that the output of the first NAND gate is an input to the second NAND gate, right? Let's maybe call this N1 and let's call it N2. So the output of N1 is an input to N2, and the output of N2 is an input to N1. So that's the reason we call it a cross-coupled NAND gate. So let's see how it works. The way that it works is something like this. So let us assume that S is equal to 1. So we're trying to set the value of Q to 1. We are setting R to be equal to, so we have R as 0. So what happens? If S is 1, so this particular value over here is 0 because it's a complement of S, and since R is 0, the value here is 1. So in any NAND gate, whenever one of the inputs is equal to 1, then the output, in any NAND gate, when one of the inputs is equal to 0, then the output is equal to 1, right? Because it is not possible that the AND condition will be true. So as a result, if one of the inputs is 0, we can happily write the output to be equal to 1. So since this is 1, 1 comes over here, and the NAND of 1 and 1, so AND of 1 and 1 is 1, so the NAND of 1 and 1 is 0. So again 0 goes there, and 0 and 0, its NAND is 1. So it's a stable system. One more thing that we get to see is that in this case the value of Q is equal to 1, and Q bar, or the complement of Q, is the complement of 1, which is 0. So the first value, in a sense, we have verified. Now let's take a look at the second combination, which is the value of S is 0, the value of R is 1, so we are trying to reset it. So we expect Q to be 0, but let's verify if this is the case. So let me just erase these such that the reader doesn't get confused. Do I have an yeah, I have an eraser, so there is no reason to adopt a low-tech solution. We can adopt a high-tech solution. All right. So now what can be done? So in this case, the value of S is 0. So S complement is 1. And the value of R, we are setting it to 1. So the complement of R is 0. So the same logic holds that in any NAND gate, if one of the inputs is 0, then the output gets automatically set to 1.
Swayam Prabha. Digital India. Educated India.
So what we see is that in this case, if the reset signal is 1, the value of Q is set to 0 and Q bar is its complement, which is 1. Alright, so these two values we have verified. So what is the connotation again? The connotation here is that S stands for the set signal, and if S is equal to true, then Q gets set to 1, and R is equal to the reset signal. So if R is equal to 1 and S is equal to 0, then Q gets set equal to 0. Alright. So now let's take a look at the rest of the two combinations. So the rest of the two combinations are like this. Let me again erase the ink on this slide. Alright. Let's assume that S is 0 and R is 0. So if S is 0, then 0 complement is equal to 1, and if R is 0, R complement is equal to 1. Right? So as a result, we will not be sure about the output of the NAND gate. So it depends on what we have. So let's consider the first NAND gate. So in this case, the input is equal to the Q bar, and in this case, the input is Q. So let's essentially the question is, what is 1 and Q bar, right? And the entire thing complemented, right? So this is a NAND of 1 and Q bar. So one thing that we can see is that in a NAND gate, or maybe, let's do one more thing using the De Morgan's laws that hopefully we all know. So De Morgan's laws basically say that A and B NAND is A bar or B bar, A complement or B complement. So using this, if you open it up, this will be 1 complement, or right, so which is equal to, so 1 complement is 0, or so 0 or Q is equal to Q. Alright. So basically the output of N1 is equal to Q. And similarly, what I can do over here is that I can for the case of, so this is for N1. For the case of N2, what I can do is something very similar. And oops, sorry. So this value here is supposed to be Q, and for some reason it's Q bar, which is not correct. Yeah, that fixes it. So what we are doing here is we are computing 1 ANDed with Q, the entire thing complement. So 1 and Q is Q, so this is equal to Q bar. Right? So basically what happens is that if we set S as 0 and R as 0, which means we are not trying to set the value, neither are we trying to reset the value, then the old values of Q and Q bar in a sense continue. This is a fantastic idea, so I'll tell you why. So the way that this latch works is that we have a way of setting the value, which means setting Q to 1. We have a way of resetting the value, which means setting Q to 0 using these two combinations. And we have a way of maintaining the value, which means whatever value is there in the latch, it remains. That can be done by setting S as 0 and R as 0. So if both S and R are grounded, the latch will maintain its value essentially forever, which is exactly what we wanted to do. So naturally readers will ask what happens if we set S as 1 and R as 1. Well, so let's take a look at this. This is somewhat a tricky case, and this is a typical question that is asked in exams. So if we set S as 1 and R as 1, so S complement will be equal to 0 and R complement will be equal to 0. So moment 0 is one of the inputs of the NAND gate, the output is equal to 1. And so both Q and complement of Q will be equal to 1. So in a sense, this is an invalid input, right? It sort of produces something that we don't like, so it's invalid as an input. So you cannot set and reset the latch at the same time, so we will not consider this input at all. We'll only consider the top 3 inputs. So essentially, what are the top 3 inputs telling us? What the top 3 inputs are telling us is that we have a way of setting the latch, resetting the latch, and maintaining the value. So mind you, these are very, very important points. So it is necessary to understand these points very nicely, very clearly. And what I would advise the reader to do, the listener of this video, is to basically look at all of these combinations. There are only 4 combinations. For S and R, there are only 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. For all of these 4 combinations, work out the results the same way that I did and convince yourself that if S is 1, then essentially we set the value. If R is 1 and S is 0, we reset. Otherwise, we maintain. Alright? Okay, let's move forward. So let's now consider the idea of having a clock. So what is a clock? So basically you consider maybe for explaining a clock, the best would be to actually go out of this PowerPoint window and basically look at draw a slightly larger diagram. So consider a digital system. So a typical digital system would have millions and not millions but billions of components, right, in today's world. So there will be lots and lots of components, right? So I'm drawing these as blocks. So we'll have a lot of blocks, right? Maybe this is an adder and this thing stores, there are some SR latches here, there's a multiplier, there's an encoder over here. So let's assume that we want some data to come from the SR latch, get, from a series of set of SR latches, get added. Similarly, we want a multiplier to take that data. So we want some data coming out of the multiplier, some from the adder. We want to add it once again, right? And then we want some of these bits to choose one of. So we then want to input these bits into the encoder, and finally we are interested in the output of the encoder. So let's assume we have a circuit of this form. So clearly there is a lot that is happening, right? So when designers will design it, they need to ensure that the right input reaches the right circuit block at the same time. And with billions of transistors, this is very, very difficult. So some degree of scheduling is actually required. And if this amount of scheduling is not provided, then essentially the entire thing will go haywire. So because the latencies of these units will actually be very different. So it is possible that the SR latch takes 1 nanosecond, the adder takes 1.6 nanoseconds, the multiplier takes 2.9 nanoseconds. So actually if you see at this adder, the first input is ready at t plus 2.6 nanoseconds, and the other one is ready at 2.9. And finally, some data then again comes out. So managing the timing of all of this would actually be very difficult. So what do we do? So what do we do in school? What we do in school is that we have a timetable. And so a typical timetable, at least in an Indian school, the way it looks like is something like this, that we divide the entire school day into multiple blocks. So in India they are essentially called, at least the part of India that I am from, they are called periods. So essentially, oops, sorry. So in my school, we used to divide the entire school day into 7 periods, right? So the way that the weekly timetable was made is that, so we actually had a 6-day school. So from essentially Monday till Friday and Saturday, the way the timetable was made is that we used to have a matrix, and each matrix at this point was a period. And so then maybe the first period had maths, the second had physics, the third had chemistry, then maybe we used to go out and play football, right? So this is the way that the entire day was divided. So this made scheduling very, very easy. For example, a physics teacher could finish her second period in my class and then go and teach the third period. So let's say this is the first, second and third, could go and teach the third period in another class. So it made scheduling really, really easy. Then maybe go and teach the fifth period in another class. So how were periods demarcated? So in my school, people, they were the good old days of the late 90s. So not all the students, used to have watches, and even the watches were not in order sometimes. So what was done is that we used to have a big bell, and the bell used to sound at the end of every period. So after that, students used to rearrange themselves. So teachers used to go to another classroom. So the entire the signaling was done on the basis of a bell that used to ring at the end of every period, right? So then something used to happen, the new class used to start, again the bell, and so on. So can we have a similar bell in a digital circuit? That is pretty much, that'll be really, really useful if we have something of this nature akin to a bell. So basically what happens in the digital circuit is that we have a signal called a clock which reaches all parts of the chip. So all the logic elements will get a clock. So a clock is basically a signal which is a square wave, and so basically this is 0 and 1. So it's a square wave between 0 and 1. The duration of the 0 and 1 is equal. It's a wave of this kind. So typically the negative edge, so we'll discuss why. So when there's a transition from 1 to 0 is thought of as the bell. So all the elements inside a digital circuit coordinate themselves to the end of the clock period. So the clock period is measured from one negative edge to one more negative edge. So negative edge is when there's a transition from a 1 to a 0. So the time between one negative edge to the other is called the clock period. Right? So this time can be 2 nanoseconds, 5 nanoseconds and so on. And the number of clock periods, 1 divided by the clock period, which is the number of clock periods that you have per second, this is known as the frequency. Right? So let me call this the frequency. Alright, so the number of clock periods per second, so let's say number of clock periods per second. Right, so this is called the frequency. I'll just change the definition of the frequency. So the frequency is 1 divided by the clock period. It's not the number of clock periods, I'm sorry. Let me just quickly change the definition over here. What I want to write is something, sorry. So the frequency is the number of clock periods that you see per second, which is 1 divided by the clock period. For example, if the clock period is, let's say, 10 milliseconds, then what is the frequency? It is 1 divided by 10 milliseconds, and that is 100 times per second, which is called 100 hertz. So this is exactly the same frequency that when you go and buy a laptop or a desktop, they say that we are having a 3 gigahertz processor. What this means is that 3 billion times a second, you have a negative edge inside the chip. So this is exactly what frequency means. A frequency is the inverse of the clock period. So let's say if I buy a new machine or a laptop or a desktop, and the frequency is, let's say, 2 gigahertz, what this means is that every half nanosecond or 500 picoseconds, we have a negative edge of the clock. And all digital elements inside a processor, and including all the designers who are designing them, coordinate all their actions with respect to the negative edge of the clock. For example, let's say if there is an adder and the adder is providing its output to the multiplier, the designer of the adder will tell the multiplier, instead of specifying time in terms of nanoseconds, which will just make life hard, they say that look, the data, the output of the adder will be given to the multiplier in 5 clock periods or 5 clock cycles, right? Clock period or clock cycle, that's okay, both are interchangeable. So in 5 clock cycles, the data from the adder will be there with the multiplier. Similarly, if this data is going somewhere else and the data from the multiplier is also going to the same place, again the coordination is done in terms of the clock period. So this makes the life of designing a digital circuit very, very simple. So almost all digital circuits will have a clock. So let's take a look at what exactly happens if I have an SR latch with a clock. So when the clock is equal to 1, right? When the clock is equal to 1, so in a NAND gate, if any of the inputs is equal to 1, in this case, what will happen? The output over here is 1 ANDed with S complement, which is equal to S complement. Similarly, when the clock is 1, the output here is R bar. So this is the, if I just go back to the previous slide, this is exactly the inputs that were given to an SR latch. So pretty much here, the same inputs are being given. After that, if you want to set the value, we can set it. S needs to be 1, so Q will be 1. If we want to reset the value, we can do that. So in this case, R needs to be 1 and S needs to be 0, so Q will get set to 0. Alright. Now, let's assume that the clock is 0. If the clock is 0, then what will happen? Let's take a look at that. If the clock is equal to 0, then the output of both the NAND gates are 1. And if the outputs of both the NAND gates are 1, so let's go back to the previous slide and see what happened. If the outputs of both the NAND gates are 1, it means that S is 0 and R is 0, which is this case. And we maintain the old values, right? So basically what we can say, for a clocked SR latch, if the clock is equal to 0, we maintain the old values of Q and Q complement. If the clock is equal to 1, then this works as a regular SR latch, so we can either set the value or we can reset the value. Alright, so let's now take a look at a different kind of a latch. So typically a latch with a clock, so at least that's the convention that we would be adopting, that a latch with a clock, we'll also call it a flip-flop, right? So basically the previous one can also be called an SR flip-flop. So whenever there is a clock, we would like to call it a flip-flop. So let's take a look at a D flip-flop. So what was the basic problem in an SR latch? So there were two inputs, S and R. So typically what we were doing is that we were setting S to 1 and R to 0 to set the value, and S to 0 and R to 1 to reset the value. That was kind of complicated, so let's try to unify S and R. So let's consider a single input D and modify the clocked SR latch appropriately. Alright, so let's take a look at the D flip-flop is very, very important. So that's the reason I have this important tag. The reason it is important is that it is very, very heavily used. As the SR latch is a good latch to explain to a learner for the first time. But what is actually used much more frequently is the D flip-flop. So here is how it works. So let's consider the case when the clock is 1 and the clock is 0. So let us first consider the case, the simpler case, when the clock is 1. Well, simple and not simple depends, but let's find. If you have always considered the clock to be 1, let's consider the clock to be 1 now as well for the first, for starting to explain how this circuit works. So the clock is 1. So by this time, you would have realized that we are computing the output as 1 and D as D. So this is same as D bar. So I1 is equal to D bar if the clock is equal to 1. And if this is equal to D bar, so D bar will come over here. So what we'll compute here is 1 and which is equal to, right? So this is equal to I2 is equal to D. Alright. So in the SR latch, so then after that we have a typical SR latch. So here we can say that the value of S is essentially equal to the complement of this, which is D, and the value of R is equal to the complement of this, which is D complement. So I want to make one important point here, because a lot of students make a mistake. So let's look at the SR latch once again, the basic SR latch with a cross-coupled pair of NAND gates. So the inputs are not S and R. Okay, let me repeat it once again. It's very, very important. So let me circle this. The inputs are not S and R. The inputs are S complement and R complement. Alright? Even though we are reasoning in terms of S and R, the inputs are not S and R. They are S complement and R complement. Okay? So what is going in is S complement and R complement. Armed with this knowledge, what is going in? S complement is D complement, so S is equal to D, and R complement is equal to D, so R is equal to D complement. Fine. So what will be the output? Well, if D is 1, S will be 1, so Q will be 1. If D is 0, then S is 0 and Q is 0. So what we can essentially say is that Q is being set to D. Alright. So when the clock is 1, what we are doing is that we are transferring the input, which is D, to Q, and with a delay, of course. So that's the reason it's called D for delay, D flip-flop. And the delay is the signal passing through the logic gates. But finally, when the clock is 1, the flip-flop is enabled. So the input is getting reflected at the output. Okay? And the most important point to remember is that the inputs of this SR latch at this point, so this is the SR latch, the inputs are pretty much S complement and R complement, right? Okay. So now let me take a look at what happens if the clock is 0. Well, if the clock is 0, then 0 goes to both the NAND gates. So we have 1 and 1. So essentially S bar is 1 and R bar is 1. So the inputs are, the set signal is 0 and the reset signal is 0. So in this case, if we go back to our basic SR latch, if S is 0 and R is 0, we maintain the old values. So we'll do exactly the same. I1 and I2 will be 1, and which means set and reset both are 0 and 0. So we maintain the old values. So the working of this is exactly similar to the SR latch. It's just that we have this structure over here to ensure that we can manage with a single input. So basically what we are doing is that this is storing one bit for us. We have one input D and we have two outputs. One is Q and the other is Q complement. Essentially, logically, at least a single output. And we are saving D. So when the clock is 1, the value of D is getting stored and it is reflecting here. Then at the time of the negative edge, the value remains stable, right? So once it reaches 0, we'll maintain the value of Q and Q bar that was set. And as long as the clock is 0, the flip-flop will maintain its value. Alright, so now let's create we still haven't exploited the negative edge to the fullest extent, but let's do it by proposing a slightly more complicated structure called a master slave D flip-flop. So let's consider this circuit. It looks complicated, it's not that complicated. So let's break it down into two parts. So let's consider the master. So what is the master? It's exactly the same circuit as this, right? So exactly a D flip-flop is the master, exactly the same, and the slave is also exactly the same. So you can consider two D flip-flops where the D value goes in. There is a first flip-flop and there is the second one. So let's call the first one the master, second one the slave, and then the output Q. The catch is that the regular clock goes into the master and the complement of the clock goes into the slave. That's all. Right? So the diagram is very simple. We have two D flip-flops connected to each other. The first D flip-flop is called the master. It takes the clock as input. The second D flip-flop is called the slave. It takes the complement of the clock as input. So let's see what happens. So when the clock is equal to 1, the value of D will get transferred to the output, right? So whatever is the value of D, it will get transferred to this intermediate point because here the clock is 0. So then we'll have D dash here. D dash is equal to D, right? So the value of D moves from here to here, right? Then when the clock turns 0, the value of D moves from the intermediate point to the output, which is Q. Because when the clock turns 0, clock bar actually turns 1, right? So when the clock suddenly becomes 0, when there is a negative edge, from 1 you move to 0, the complement of the clock moves in the other direction. So since the clock here that is going in, this signal becomes 1 at this particular point, the value here between the master and the slave gets transferred to the output of the slave with some small delay, of course. So we have Q is equal to D dash, right? So what is exactly happening? If I consider this complicated circuit and I just look in the vicinity of the negative edge of the clock, initially here the clock is 1, say the value here is, let's say, D. Then just after the negative edge, the value of Q, which is the output of the master slave D flip-flop, will get set to D, right? So that's the only time in which the value will move from one side to the other side. And so that is the significance of the negative edge, that you can sort of think of the negative edge as the bell that I had in my school. The moment the clock transitions from 1 to 0, essentially whatever is there at the input of a master slave structure gets reflected at the output. Alright, So that's the idea. And then of course if I disable the clock, then what will happen is that this value that is there will be maintained. So what is the advantage of having such a structure, a master slave D flip-flop? Well, the advantage is like this. So it'll be clearer actually in chapter 9, but I can give a little bit of a preview. So the advantage is something like this, that we can create a structure. So typically what will happen while designing a large processor is that we will have to save some values in D flip-flops. So let me call this an FF. And then at the beginning of a clock cycle, which means at a negative edge, the data will come at the outputs of the set of flip-flops. We'll then have a set of logic gates. So it's typically represented as a cloud like this of logic gates. They'll compute their value within the clock cycle, and before the next negative edge, the values will be ready, and they will then be stored in the flip-flop, right? In one more flip-flop, right? Because they'll be ready just before the negative edge. So then they'll be stored, and then in the subsequent clock cycle, they will be available at the outputs of this flip-flop. So this is a very, very important design strategy of digital circuits. It is called pipelining, and we'll discuss all the advantages of pipelining in chapter 9. But the only thing that the reader or the person who's listening, watching this video needs to appreciate is the following. So let me again go back actually to my journal. So the only thing that the reader needs to appreciate is that if this is a master slave D flip-flop and this is the input and this is the output and this is pretty much the clock, right? So basically at the negative edge of the clock, the output gets set equal to the input. So the input needs to sort of become stable slightly before the negative edge. So let's assume that at this point the input becomes stable, then the clock transitions from 1 to 0, and that's when the output of the flip-flop reflects the input. And the value in the flip-flop can stay for as long as we want. We can disable the clock. So in this case the value will remain. Or we can set no, I think the only way is by disabling the clock, otherwise the input will always reflect at the output, right? For a D flip-flop there is no other way. For a SR flip-flop we can set S and R to 0 and 0, so that would maintain the value. But in the case of D flip-flop we can disable the clock and the value will be maintained, right? So we can store the value. That's the basic idea of what a D flip-flop does. This is a very, very important logic element that we'll be using in chapter 9 mostly, but at least we should take note of it now. Alright, so let's move. Let us now consider a similar circuit as the master slave D flip-flop. It's called the master slave JK flip-flop. It's slightly more complicated than that. So let us first decompose the design into parts that we already know. So as we see, let's divide the design into two halves, the master and the slave. So the first part is a regular SR latch, a clocked SR latch with a little bit extra. But the second part is exactly a clocked SR latch, right? There's no difference, right? So the second part is completely a clocked SR latch with the complement of the clock going in. And the first part is also a clocked SR latch. The only difference is that in this first AND gate, instead of two inputs, there are three inputs. That's the only difference. The same is true of the second AND gate over here. So the interesting part is that this input is actually Q, complement of Q, which is coming in, Q bar. This is what is coming in. And similarly here, the complement of Q is coming in. The value of Q is coming in, which is Q itself. So that is the only difference. The only difference is that this is exactly the same as a master slave SR flip flop. The only difference being that the first two NAND gates uh, actually take three inputs. Okay, the first two NAND gates take three inputs. The inputs are Q bar for the first NAND gate that takes an input J. And so the inputs here are called J and K, not S and R, but J and K. So the input where the J is coming, uh, the other input is Q bar, and for K, the other input is Q. That's all. And the third input is the clock. So let us, this is also a negative edge triggered system. So there is a positive edge and then a negative. So let's consider the case when the clock is 1. So when the clock is 1, the master is active and the slave is not active. The slave is maintaining its values. So we'll not consider the slave. So let us consider all the cases when the clock is 1, which means that we only need to consider the master. So let us consider each of these cases. The cases are simple. So the first case is when J is 0 and K is 0, right? 0 and 0. So this is a very simple case. So if J is 0 and K is 0, then if one of the inputs of an AND gate is 0, then the output is set to 1. So with no difficulty we can set I1 to 1 and we can set I2 to 1. No difficulty at all. So if I1 and I2 are 1, what we will have is essentially this is S bar, so set and reset both are 0. So the values, whatever values were there, they will be maintained. So what value was there? The old value of T1. So T1 is essentially we're using T1 to label the value at this wire. It's not a separate structure. So what was the old value of T1? The old value was of T1 was the same as Q, right? So basically whatever was in Q was in T1 because so let's just consider what happened before this clock cycle. So before this particular clock cycle, we had a positive edge. So at the time of the positive edge, when the clock was 0, the value of T1 was reflecting in Q, and once the clock became 1, the slave got disabled. So the old value of T1 that we have over here is essentially the same as the value of Q. So as a result, since we are maintaining, the value of T1 that we have is the same as the value of Q. Alright. So this is when the clock is equal to 1. Just prior to the negative edge, so just prior to the negative edge, essentially we are considering, let's say, this instant of time. So let me maybe draw a slightly bigger figure. So we are essentially considering, let's say, this instant of time slightly before the negative edge. So what we are saying is that if J and K, both of them are 0, then the value at this point, which we call T1, will be the same as Q. Why do we say that? We say that because the value of I1 and I2 are 1 each. So the latch will maintain its value. So T1 will be the same as the old value of T1. What was the old value of T1? Let us consider this point of time. So what was there in T1 got reflected in Q. So basically T1 is the same as Q. Alright. Okay, so we have considered this case, which tells us that if J and K are 0, both of them are 0, then the value of T1 will be the value of Q. And what point of time are we considering? Just before the negative edge. Now let's consider one more combination. Let us consider the next combination in which J is equal to 1 and K is equal to 0. So if J is 1 and K is equal to 0, so let's consider what we can do very quickly, and the clock is 1, of course. What we can do very quickly is that we can set the output of this NAND gate to 1, because the moment we have a 0 as an input, the output of the NAND becomes 1. So I2 is equal to 1. So what's happening over here? So what's happening over here is that we are getting Q bar here, right? So the output I1 is equal to 1 and Q bar, entire thing complemented, which is equal to Q, right? So I1 here is equal to Q. Okay. So basically what we see is that I1 is equal to Q and I2 is equal to 1. So how do we solve this? The way that we solve this is that we consider two values. We consider for both cases Q being 0 and Q being 1. So let us consider so this value over here is 1. So let us consider the first case when the value of Q is 0. If the value of Q is 0, then the output here, because since this is an AND gate, is equal to 1, so T1 is equal to 1. Alright? So when Q is 0, T1 is equal to 1. Okay, so we consider this case Q is 0. Now let's consider the next case, which is Q is 1. So let me just maybe erase. Let us consider the next case where Q is equal to 1. So here Q will be equal to 1. So if you have 1 and 1, so essentially both set and reset are 0, so the value will be maintained. So the value that will be maintained, what will we have is the same as this case, which means T1 is equal to the value of Q. And what is the point of time that you're looking at? Just before the negative edge. So whatever is the value of Q, T1 must have been equal to that. And since the value of Q is equal to 1, T1 is equal to 1. So we see that in both cases, T1 is equal to 1. Alright, so what is happening? In the J terminal, if it is set to 1 and if K is set to 0, then irrespective of the value of Q in all cases, the value at this point T1 is being set to 1. Now let's consider the next combination. So let us consider the next combination in which J is equal to 0 and K is equal to 1. So if J is equal to 0 and K is equal to 1, so what this allows is that we can nicely set the value of I1 to be equal to 1. Right, so this case is covered. What is then not covered is basically this, that what is the value of I2? So since the clock is equal to 1 and we are getting Q over here, value of I2 is Q and 1 and 1, entire thing complemented, which is Q bar. Alright, so basically the value at this point is the complement of Q and the value at this point is 1. So let's do the same thing. Let's follow the same logic as we did before. Let's consider two cases. Let's consider the case where Q bar is equal to 1 and when Q bar is equal to 0. So if Q bar is equal to 1, so we'll have 1 and 1 as both the inputs. So the value will be maintained. So whatever is the old value of T1 and T1 bar, the same value will be maintained. So what is the old value of T1? It is the value of Q. So since Q bar is equal to 1, Q is equal to 0. So in this case, when Q bar is equal to 1, T1 is equal to 0, which is the value of Q. So let us now consider the other case. So let me just erase some of the temporary values and let's consider the other case when Q bar is equal to 0. So if Q bar is equal to 0, then this particular point is 0. And so nicely we can figure out the output of the AND gate, which is 1. So 1 and 1 here is 0. So we see that for both the cases, irrespective of the value of Q, the value of T1 is 0 in this case. So we write 0. So we can think of J and K as pretty much as S and R. If J is 1 and K is 0, the value at the middle between the master and the slave is set to 1. Similarly, if J is 0 and K is 1, the value of at the point T1 is set to 0. So mind you, I1, I2, T1 and T1 bar are essentially points. We are just referring to the values on certain wires. So let's now consider the last case. The last case is very interesting. So in this case, J is 1 and K is 1. So if J is 1 and K is 1, what do we have? We have the clock to be 1, J is 1 and K is 1. Alright, so the value at this point is Q complement and the value at this point is Q. So the value of I1 is essentially Q complement and 1, entire thing complemented, which is equal to Q. Right, so the value of I1 is equal to Q. And the value of I2 is essentially Q complement, which is Q bar. Given the fact that we have Q over here and we have Q bar over there, so essentially what is the set symbol? The set is, so mind you, S bar is equal to Q, which essentially tells us that S is equal to Q bar, and R bar is same as Q bar, so R is equal to Q. So taking both of these in our SR latch condition, what we can see is that the value of T1 is the same value of the set, is the same as S, which is Q complement, and the value at this point is Q. So what we have effectively done is that we have replaced this with Q complement. At what point? At the point which is just before the negative edge. We have the value of T1 as Q complement. So we can think of it as a toggle, as like a bit flip, right? So let me explain the logic once again. So what happened is, since all the values were 1, so Q complement was coming here, Q was coming here. So basically this can, if you think of the SR latch, this particular point is actually the S bit and this particular signal here is the R bit. So the S is being set to Q bar and R to Q. So the outputs at the end of the SR latch will essentially be Q complement and Q. So we are effectively toggling, doing a bit flip of whatever is Q, we are setting T1 to be the complement of Q. Fair enough. So now let's again clean the screen. So what is it that we have here? What we have over here is that we have looked at the point of time which is just before the negative edge, and at this particular point of time, for the 4 combinations of J and K, when J and K are 0, 0, we have essentially we maintain the value. If J is 1, K is 0, we set the value. If J is 0, K is 1, we reset the value. The interesting case which we have not seen up till now is when J is 1 and K is 1. In this case, what we do is that we essentially toggle the value of Q, or we essentially flip the value of the bit. After this, we have the negative edge, so the clock becomes 0. So the master becomes disabled and the slave becomes active. Once the slave becomes active, we enter a new clock cycle, right? Because it's after the negative edge, so we enter a new clock cycle. So in this case, what we need, so this is a regular SR latch, no problems. And since the clock is 0, so basically we are considering clock bar. So clock bar is equal to 1. So the slave is enabled. So let's consider the value of T1, which is so T1 and T1 bar. So essentially, this is we are either trying to set or reset the SR latch. So in this case, what did we have when j and k were 0? The value of t1 as q, but that was in the previous clock cycle. So let's refer to it in the current clock cycle as old q, which is which point of time are we considering? It is just after the negative edge, right? Just after the transition. So now we are considering that the negative edge has happened just after the transition in a new clock cycle. The value of t1 is the old value of q. The value of t1 when j is 1 and k is 0 is 1. When j is 0 and k is 1, the value of t1 is 0. And an interesting case, when it's 1 and 1, it is the complement of old q. So what does the SR latch do in this case? Well, what it does is very simple. It just transfers the values at its input to the output because it's enabled. So that will take some time, but the time is minimal. So all the values at the input will get transferred to the output. So what is it that we get to see? What we get to see is that when j and k both are, so let me maybe clean the screen. So what we get to see after the negative edge, when the new clock cycle begins, is that if j and k are 0, the jk flip-flop maintains its value. The value of q is the same as old q. So what do we mean by old q? At the end of the negative edge, the new cycle starts. So at this point and this point, so this is where we'll have old q, and this is where we'll have new q. So new value of q is same as the old value of q. If j is 1 and k is 0, we are setting the value, setting q to 1. If j is 0 and k is 1, we are setting q to 0. If j is 1 and k is 1, so this is the interesting case, there we toggle it. So the value of the output is the inverse, is the bit complement of the previous output. So we are essentially doing a toggle over here, a toggle. Alright, so this ends our discussion on flip-flops. The important points that should be remembered are as follows. So the important points are that we have the notion of a clock. Why do we need a clock? Well, we need a clock the same reason because I had a bell in my school. It is essentially to synchronize different logical elements such that if all the inputs are ready by the time that we have the negative edge of the clock, right? So we are assuming a negative edge triggered system where at the time of the negative edge a new clock cycle starts. So by this time all the inputs are ready. The moment a new cycle starts, if you consider this to be a flip-flop and this as the inputs rather, and this as the output. So the moment we have a negative edge, the inputs get transferred to the output, and we have a way of maintaining the value, storing the value in the flip-flop even across clock cycles. For example, in JK flip-flop, we set J and K to 0, then the value will get maintained across clock cycles. So this is essentially a storage structure where the inputs get reflected at the output for at the time that there is a negative edge, and in a general condition the value is saved in the structure till the next negative edge. So with this we can create a lot of sequential logic, we can create counters, and we can create frequency dividers, we can create a host of digital circuits. So I would like to ask the reader to look at any classic text on digital logic. So they'll find lots and lots of examples with flip-flops. You can also take a look at books on switching theory, such that you have a slightly deeper understanding. So the book by Z. Kohavi is one such reference where we discuss switching theory and a lot of applications of sequential circuits for doing fairly complicated logic. So for example, you want to make a traffic light controller. How would you do it? You'll essentially have a set of flip-flops, and you'll have a clock, and then pretty much there'll be a set of inputs, and there'll be data moving between the flip-flops, and you can sort of realize complex logic with the help of that. So I'll not discuss this more. So our main aim in this chapter is to provide an overview. So then we will move to the next part of the lecture, which is memory cells. So what is a memory cell? In the memory cell, we can essentially store a lot more data in a in a fairly compact form. And so in a flip-flop actually requires a lot of transistors. It's a very nice and fast structure, but it requires a lot of transistors. As compared to that, a memory design is far more compact. So for the same area, it allows us to save far more data. So we'll take a look at memory cells next. So we'll do this in the next lecture.